So in this lecture, I'm going to finish out section 2 of this chapter on exponentials and logarithms, and hopefully do a little bit of section 3. So we previously in class had gone over the inverse and one-to-one properties of these functions, the two gray boxes here at the top of the beginning of 6.2. The inverse part is just telling us that logarithms and exponential functions are inverses of one another. For both of them, you have a base. The base literally is the base of the exponential, but we call it the base when we talk about the log base b of some number c. Anyway, one-to-one properties essentially tell us that we can kind of cancel off logs and bases from both sides of an equation. If I have something like 2 to the x power is equal to 2 to the third power, well, that leads me right to saying that the x has got to be equal to 3. That is, you can think of it as you just get rid of the 2's, the bases of these exponentials. Similarly, if I'm writing the log base 10 of say, x plus 1 was equal to the log base 10 of 42, then I could just, again, similarly think about canceling off the logs, and it would tell me that x plus 1 was 42. So I guess x would have to be 41. Well, the thing that remains for us to do is understand two more things out of this section. One I began, but I think I'm going to take it fresh and completely reintroduce this. The 3 different algebraic rules that are applied with exponentials, and then there are corresponding things with logarithms. So let's start with this first one, that if you have b to the u times b to the w, that is the same as b to the u plus w. I would like to express this by sort of, well, a little abusive notation, but when you say b to the u, you mean b times itself a bunch of times. And how many times would be multiplying it by itself? It would be u copies of b. And when you say b to the w, it's kind of the same thing. You're going to have a bunch of b's multiplied together. B times dot, dot, dot times b. And in this guy, there's going to be w copies. So the point of this rule is just to say, well, yeah, okay, that means if I put these two things together, there's u copies and then there's w copies. That's adding. There's u plus w copies. Right? So yeah, that rule is fairly obvious when you see it this way. The problem with that rule, as stated, though, is it looks like it's for whole numbers, one thing, and it looks like it's for only positive numbers, really. I've got to think of, if I'm going to have some number of copies of b, I'm really talking about positive numbers for u. But we can understand negative exponents and we can understand fractional exponents, and they obey these same rules. All right. Well, let's move towards getting negative exponents first. To do that, think about this version of the rule, or the rules. If you have b to the u times b to the w, well, that means there's u copies in the top, right? And then there's w copies down below. And if u is bigger than w, what'll be left? It'll be, well, for each one of these w's copies that are down in the bottom, you'll cancel it with one of the b's that's in the top. It's going to look something like, let me just do it schematically. Suppose we had 5 b's in the top and only 3 b's in the bottom. Well, we would cancel the b's that could be canceled, and we'd be left with some number of b's. Well, what is that number? It's the difference. This is b to the u minus w. So that's the second rule that's given here in the book, the quotient rule. It says it first in terms of the generic function f, which is b to the x, but it's better when you see it applied to actual numbers. B to the u divided by b to the w is b to the difference of those two. Now, let's look at that in one particular case. So we have, let me write it. I kind of prefer to see this on the other sides of one another. That is the fraction b to the u over b to the w on the left, and that's equal to b to the u minus w. What if u and w are equal? What happens then? Sorry, working off the bottom of the screen. Sorry about that. If u and w are the same, then the number in the top and the number in the bottom are the same. And if you divide a number by itself, you just get 1. And then if you look at the difference, if u and w are the same, you get b to the 0. Now, notice that that is done sort of generically with no particular value of b in mind, right? B was just a letter. So this is why any number to the 0 power is 1. It's really a consequence of this rule about how quotients work with powers. Another thing you can see from this quotient thing is how to deal with negative exponents. Let me just say negative exponents and then give an example of this. If I have something like, I don't know, b to the 3rd divided by b to the 7, according to the rule, that would be b to the 3 minus 7. Yeah, and that's b to the negative 4. In other words, we've got a negative power on b. What's that really mean? Well, that comes from thinking about that thing and the cancellations you can do. B to the 3 over b to the 7, that's 3 b's in the numerator and 7 b's in the denominator. Kind of wishing I'd used a smaller power. All right, yeah, 7 of them downstairs, 3 of them upstairs. Bunches of them cancel, but we've got 4 b's left in the bottom. Right? So that's b, well, no, it's not really. It's 1 divided by b to the 4th. It turns out that that's what we use as a way to understand the meaning of a negative exponent. If you see b to some negative power, it just means the same power positive in the bottom of a fraction. Okay. Now the remaining rule that's on that sheet, on that page of the book, is called the power rule. They say it first in terms of, again, a function, but I believe if you look at the specifics of it, it's better. What do you get if you raise a power to yet another power? So b to the u raised to the w. Well, here's what you should think about it as. No, you know what? Let's not be generic. Let's do it for a particular case. Let's do an example of this, and you'll get the idea. Suppose I had b cubed squared. Fairly small powers, right? Well, b cubed means b times b times b, yeah? So that's times itself. B times b times b, 3 copies of b squared. But when you square a thing, that means that thing times itself. B times b times b times b times b times b. I don't know. How many b's are there total in that mess? 6 of them. Do you see that that's the same as b to the 2 times 3? Kind of the only other option is that maybe it's 2 plus 3. Well, no, it's not. 6. So the product is the appropriate thing to do. If I did this with a tougher example, suppose I had made this 4 up here. Then we would have b times b times b to the 4th power. And then we would need 4 copies of b times b times b. Shoot. B times b times b times another b times b times b. How many b's total have I done when I wrote b times b times b cubed to the 4th power? Well, copies of b times b times b. That's multiplying, isn't it? Yeah, so we've got 4 times 3 or 12 copies total. Yeah, in other words, when you're raising a power, you should multiply the exponents. When you're raising something that's already an exponential expression to another power, multiply the exponents. Okay, like I said before, each one of those rules has a version that has to do with logarithms. And I'm not very happy with the way the book has done this. So I'm gonna say it slightly differently. In fact, they've got x introduced as the generically, the input to a generic function that happens to be logarithmic. Logarithm base b of x is g of x. I'm going to use x for a different purpose here. And I'm also going to use y also for a different purpose. These are not the usual x and y that we get when we talk about the xy plane. So what I want to do here is kind of name the thing that we write b to the u power. And that's why I need x. B to the u is going to be x. And b to the w, that's going to be y. Just name calling for the moment. Why am I doing that? Well, each of these exponential expressions can be re-expressed in terms of logarithms. So these would be logarithms base b. U is the power on b that will give you x. In other words, u is the logarithm base b of x. And similarly, the logarithm base b of y would be w. That's clear. This is me saying just make it so. We're going to choose x and y to be those powers of b. But this is just a restatement of what that means in terms of logs instead of in terms of exponentials. Cool. Well, in the power rule as it was stated for exponential functions, we had b to the u plus w equals b to the u times b to the w. Let's just put that in a box. B to the u plus w equals b to the u times b to the w. Where have we seen those before? That's the junk I just called x and y. So b to the u plus w is equal to x times y. Now re-express that in the logarithmic way. Well, this is a certain power on b, which is apparently the power on b that you need in order to get x times y. So if you rephrase that in terms of logarithms, it says that the logarithm of xy, x times y, right? That's equal to u plus w. Why did I write w? I want to say u plus w. That looks weird. U plus w. Now it's better. I kind of darkened it in. Huh. And what's u? Look above here. U is the log base b of x. And what's w? That's the log base b of y. So, oh, I left out the b on this log. Log base b of x plus log base b of y. Yeah, so what that says to me is this. If I have the logarithm to any base of a product, things get easier with logarithms. You get the log base b of the first multiplicand added to the log base b of the second. Let me just give you a trivial example of this. If we're in base 10, b is 10. That would be something like log base 10 of, say, 100 times 1,000. Now, according to the rule, this is saying that should be log base 10 of 100 plus log base 10 of 1,000. I'm just going to say question mark over that equal sign though. Why am I questioning that? Well, these are two things that I know. Log base 10 of 100, that's 2. And log base 10 of 1,000 is 3. So here we are in college doing 2 plus 3 is 5. Cool, but what about this? Well, go ahead and do the product inside there. That is 100,000. How many zeros are in 100,000? Sure enough, 5 of them. And that means we've just verified this question I was asking. It's true that log of 100 times 1,000 is log of 100 plus log of 1,000. That's the way logarithms work with products. How does the quotient rule get reinterpreted? This is less, I don't think we need to go through the full argument because we just saw it work for multiplication. How's it going to play out for division? If I have the logarithm to any base of a quotient, division is going to turn into subtracting. So we'll get log base b of the top minus log base b of the bottom. Fun stuff. And finally, powers. How are powers going to work? Well, this one, again, I'm not sure I want to go through the argument as to why. It's actually pretty easy if you just think of it in this heuristic that I've said a few times. Logarithms make operations one notch easier. So what are they going to do to powers? One notch easier than powers is multiplication or division if you've got negative powers, I guess. Anyway, what does this mean for us in terms of logarithms? Log base b of x to some power n just turns into multiplication. The only funny business here is one number gets left behind inside a logarithm and the other number gets pulled out as a multiplying factor. It's the power that gets pulled out, and then you leave behind x in the logarithm. So do you see what that looks like? It looks as if we just said, hey, take this n here and pluck it out front and put it in front of the logarithm expression. That is, if I had log base 10 of, 2 to the 5th power, I could just pull that 5 out front and take the log base 10 of 2. Get the same number. I'm going to pull out a calculator, which I had handy, here it is, and just verify that for us. What is 2 to the 5th power? I shouldn't need a calculator for that. That's 32, right? So log, well, I should show you where the button is. If you get one of these TI calculators, it's on the left-hand side. There's log, there's ln. It's interesting to notice that e to the x and 10 to the x are on the same buttons, but you have to hit the second key to get them. Anyway, logarithm of 32. Okay, 1.5051499. Let's say 1.5, close enough. On the other hand, that's supposed to be 5 times log of 2. There you go. That's the same number we just saw, isn't it? So yeah, it worked in that one case, but trust me on this, it works in general. If you have a power, you can pull it out front and it becomes a multiplying factor instead of a power. A notch easier. Okay, finally, in this section, I want to show you, let me just recommend that you go through using these rules through some of these examples. I'm not going to, okay, maybe I should do one. See this example, 6.22, 6.22, 6.2.2 is what it is. They have, I'm just going to look at number 2 to give you a sense of this. What the instructions here say, use the properties of logarithms to write the following as a single logarithm. Now this is a nice one because it uses all the rules. We've got this is an example of use here. We've got the logarithm of x plus 2 times the logarithm of y minus the logarithm of z. Cool. Let's point out that the 2 up front of log y looks like it just got plucked out from the inside. If I'm trying to write things as single entities, I can put it onto the inside again. That is, this rule is reversible. I can either pull the 5 out, that's the power outside, or I can take a multiplying factor that's outside and bring it inside, but it becomes a power. So this is log, let me just copy everything, log of x plus log of y squared minus log of z. Now I'm inclined to do everything at once here. We've got a sum of logarithms and then subtracting a logarithm. That turns out to be, the sums turn into products. So we got x times y squared. And subtraction, that's division inside the log. You see how easy that is to turn a complicated thing with multiple parts into a log of a single quantity. And then you might use the one-to-one business to say that x times y squared over z is equal to something else, right? We're putting that in use. So the last thing we're going to need in this section is called the change of base formula. Now, they do the change of base formula generically, and I'm not real crazy about that. I want to show you 2 different versions of the change of base formula. One of them for log base 10, and one of them for natural log. If I have the log base 10 of some number x, and I want to get it, and I want to figure out the log base something else of x. Well, what I just wrote is wrong. Let's say versus. I want to compare log x versus log base something else of x. Let me show you a Desmos graph that I've already pre-made. That's a graph. The red one is log of x, log base 10. You can verify that easily enough. It goes through the point 1, 0, as all logarithms do. And look, this other point that's on the graph is 10, 1. Meaning if you take the log base 10 of 10, you have to get 1. What's the power you stick on 10 to get 10? 1. Yeah. The other 2 graphs I've got here are the natural log in green and the log base 5. Now, Desmos does allow you to do logs to funny bases, but if you've got a calculator, the only logarithms the calculator has are log log and natural log. So if you want bases other than that, you have to know the change of base formula. So how does the change of base formula work? Well, the easiest way to say this is that all logs are scaled versions of one another. The logarithm to any base is just a vertical scaling of some standard one. We could use the green guy or we could use the red guy. I'm going to use the green guy. We'll try to match these other guys to the green guy by throwing in a scale factor. So wait a minute, put the green one on top. Log base 10 is much shallower. If I throw a constant k in front of this guy and add a slider for that, well, when k is 1, of course, I'm just seeing log 10. But if I bump k up, I can make this graph coincide with the green graph. 2.3. Where did the value 2.3 come from? I don't know. How about the log base 5? Let's make a scale factor on that. This is an outside change, so I'm talking about a vertical scale factor. If I need to scale that one up until it is on. Boy, it doesn't want to. All right, I'm going to change the setup a little bit. 0 to 3 should be good enough. Now the action will be a little smoother. All right, looks like it's about 1.62. So 2.3 was the right scale factor to turn log base 10 into natural log, and 1.62, that was the right factor to scale to make log base 5 look like natural log. Another way to say this is that the logarithm base b of x can be gotten by something times log of x. It turns out that something, though, is better thought of. I'm writing where it's invisible. I'll say it again while I'm pointing at it. Log base b of x is something times log of x. What the something is, though, is actually 1 over something. This is 1 over the log base 10 of the base b. Or if I said this in terms of natural logs, the log base b of x would be the natural log of x, again, times something, times a scale factor. And that scale factor turns out to be 1 over the natural log of b. Or stating both of these a little more succinctly, if I want logarithm to some funny base b of x, what I do is take the natural log of x and divide by the natural log of the base. And similarly, if I want to get this using base 10 log, well, take the log log and divide it by the log log of the base. Now I'm going to put that in action for you because I think that's somewhat unbelievable, I think, at first. Lost the focus here. Come on, focus for me. All right, so the let's say we wanted to get the log. Let me just do it for the natural log for a second. Suppose I wanted the natural log of 5. Now, this calculator does have a natural log button on it. Okay, so not a problem here. But supposing I didn't have that thing, I could use the log log to find it out. I would just take the log log of 5 and divide that by the log log of the base of that expression, which is e, 2.7182. Well, this is not quite the same number in all its decimal places because I only put in 5 of the decimals of e. If I was being a little smarter, which I should have done, let me try this a second time. Instead of putting in what I remembered of the decimals of e, I should have gone to the button for e, which is right over here on top of the division sign. Second in that, and then that should do the trick. Now you see that's exactly the same, 1.609, 437, 912. 1.609, 437, 912. So if you want base any power logarithm, you can use this change of base formula. Maybe one last example I should give you. You should know that 3 raised to the 4th power is 81, right? So that is, if I wanted the log base 3 of 81, it'll be equal to 4. So let's get a log base 3 using log. Log of 81 is that number divided by log of 3. Wow, 4. Yeah, so that business works. The change of base formulas is a very, sorry, I left a mechanics behind the scenes thing showing up there. Anyway, yeah, the change of base formula is quite useful, so it's something we're going to want to remember. The only difference between what I've done here, where there's a LOG version and a LN version, is, and what's in the book, is they're saying you really can do this for any base. That is, choosing LOG or choosing LN as your standard base. That's fine if you want to, but you could make anything be your standard base. If if humans had 5 fingers, we might make base 5 be anyway, yeah. So you could say this in a slightly different way, in more generality, which is what they've done here. The logarithm base a of any number x is, take the logarithm base b of x and divide it by the logarithm base b of a. The standard base is logarithm of the base of the other log expression you're trying to get at. All right, so that's the end of 6.2, and I think that's a perfect place to put an end to things. So I'll see you on Monday.